All right, so yesterday when we finished off, we were talking about distance formula and midpoint formula, right? So we looked at how to use the distance formula, but I mentioned to you today, I wanted to show you why the distance formula worked the way that it did, look a little bit like at the proof of the distance formula. So here's the formula that we were using yesterday. I think we get this idea that way long ago in the dark ages, they had nothing to do but sit around by candlelight with their quill pens and their ink and just make up random math formulas to torture us with today, right? Actually, most of the math formulas that we have come from other formulas that we have, and that's the case with the distance formula. The distance formula just comes from the Pythagorean theorem. Let me show you what I'm talking about. If I'm trying to find the distance between these 2 points, you'll notice that I could make a right triangle out of that. And of course, with the right triangle, I could do Pythagorean theorem, a squared plus b squared, in this case, would equal d squared. I'm going to call that distance d for my hypotenuse. So if a squared plus b squared was equal to d squared, and I want to know just the plain distance, I would take the square root of both sides, and I would figure out what a and b were equal to. Well, if I come over here and look at a, if you'll notice, a is just the distance or the length from x1 to x2. It's just the change in x. If this were 5 and this were 1, I could say 5 minus 1 is 4 to find the length of a, right? So it's just going to be the second x value minus the first x value. So let's replace a with the second x value minus the first x value. If I were trying to find b, that's just the vertical distance. That's just the change in my y values. So again, if this was like 4 up here and this was 1 down here, I would say 4 minus 1 is 3 to figure out that distance. So it's just going to be the change in my y values. So if I replace a with the change in x and b with the change in y, I want to know what plane d is, not d squared. So undo that square by putting a square root on both sides, and magically we have created the distance formula, right? Just a version of the Pythagorean theorem. So the nice thing about understanding where it comes from is I am horrible at memorizing things. I can't keep it straight to save my life. I'm forever trying to put a subtraction sign here or an addition sign here or something like that. So if I understand where the formula comes from, it makes it easier for me to remember. Because what's going to happen is on your test, I'm going to give you a matching formulas page. And so I'm going to give you 4 or 5 different variations of this formula, and you'll have to choose what's the correct one. And, you know, some of them might have a minus here, or some of them might have a plus here, or some of them might not have the square there, or something like that. And if I look at it and we're like, oh, I knew the distance formula, but all these look the same, and I don't know which one it is. If I remember, hey, it comes from the Pythagorean theorem, and the Pythagorean theorem is a squared plus b squared, there's no way I'm going to think that middle sign's supposed to be subtraction. And if I think back to, okay, how did we get a? Well, it was just the second x value minus the first one. Oh, yeah, okay, well, that's got to be subtraction then, not addition. Or it's got to be a squared plus b squared, so those squares have to be on there. All right, so let's look at example number 6. We left off yesterday with example number 5, so let's pick up with example 6. It says, show that these 3 vertices are the vertices of a right triangle. All right, if this ABC, if this is a right triangle, then what has to be true about it? If it's a right triangle, what has to be true? Has to have a right angle. Anything else? What else is true about right triangles? We know about the angles that one has to be right. What do we know about the sides? Hypotenuse. Has to have a hypotenuse, yes. What's the relationship of the sides?
A squared plus b squared equals c squared.
Perfect. A squared plus b squared equals c squared. Has to have that Pythagorean theorem, right? So if I could do a squared plus b squared equals c squared and it work, it's a right triangle. If it wouldn't work, then it wouldn't be a right triangle, right? So I need to figure out the length of a, b, and c. The legs of that triangle. Well, I know how to do that. That's just distance formula, right? So here's some really good review of what we were working on yesterday. Let's go through and let's find the distance between these 2 points for A, the distance between these 2 points for B, and the distance between these 2 points for C, and then we'll see what we end up with. All right, let's do the first one together. If I'm trying to find the length of A right here, I could go through and I could say, okay, change in X, 5 minus 2. And then change in y, 7 minus 1. And that would give me 3 squared, which is 9, and 6 squared, which is 36, so square root of 45. Not even going to bother to simplify that radical down because I'm about to square it in a second in the Pythagorean theorem anyway, right? So I'll save myself the work. All right, you try B and C and see what you get. All right, so what'd you get for side B when you found that distance?
Square root of 5.
Square root of 5, perfect. We did change in x, change in y, squared those values, absolutely, square root of 5. How about what'd you get for C?
Square root of 18.
All right, so if we go through and we've got difference in x's, difference in y's, we would end up with square root of 50?
Sorry, I actually multiplied 7 times 2.
Oh,
So,
no problem.
Sorry.
No problem at all. So square root of 50. So how do I know which of those is the hypotenuse? Because it matters when you put it in Pythagorean theorem, right? Hypotenuse has to go in for C, so how do I know which is the hypotenuse?
The longest one.
Yeah, it's always the longest side. So which of those is going to be my hypotenuse? Square root of 50, perfect. So let's try throwing that into our formula and see what happens. Doesn't really matter if I put square root of 45 here or square root of 5 here. Put the other one here, but it does matter that I put square root of 50 over here in the slot for the hypotenuse. So a squared plus b squared is equal to c squared. All right, so we simplify that, and I get 50 equals 50. So what does that mean? Is this a right triangle or not?
Yes.
Yes. If the Pythagorean theorem works, then yes, it's a right triangle. If the Pythagorean theorem had not worked, if I'd gotten something like 35 equals 50, then I would say, no, this is not a right triangle. All right. Example number 7, they ask us to find midpoint. We actually went ahead and did that yesterday, so let's look at example 8. For example 8, it says we've got a real-world application. You can see that icon up there. So here's where what we're looking at might show up in an everyday situation. Winn-Dixie Stores had annual sales of $1.3 billion in '96 and $1.36 billion in 1998. Without knowing any additional information, what would you estimate the 97 sales to have been? Anybody? What would you estimate them to have been? 1.33 billion. Yeah, I would say that's probably a good guess. How'd you get that?
Because it's halfway in between 1.3 billion and 1.36.
Halfway in between 1.3 and 1.36. So in essence, we just used common sense, but what we did was the midpoint formula. Because what we said is, okay, if I need what's halfway between 1996 and 1998, that'd be 1997. Then I need what's halfway in between 1.3 and 1.36 billion, which is 1.33. If I had gone through and done the midpoint formula and I had added my two x's and divided by 2, I would have gotten 1997. If I had added my two y's and divided by 2, I would have gotten 1.33. So they gave us that example for us to see that, you know, I may not officially throw this into the midpoint formula, but I can see why that would work. And it helps me understand better the midpoint formula itself and why it works the way that it does. All right, so let's talk about circles to finish off today. Looking at the equation of a circle. All right, so to begin with, the equation of a circle in standard form is x minus h squared plus y minus k squared is equal to r squared. Here's another one of those formulas that did not come out of the clear blue sky. We get the equation of the circle from the distance formula. Let me show you how. When you're working with a circle, we typically refer to the center of the circle as HK. Any point on the circle, we could give an ordered pair XY. And the distance between the center of the circle and any point on the circle is always going to be the radius, right? So if I found the distance between HK and XY, that would be my radius. So let me do that. I'm going to use the distance formula for these 2 points to figure out what the length of r is. So I could say, okay, if I go through and say my distance is equal to the square root of x2 minus x1. So I could say, okay, x2 minus x1, x minus h. All right, then I need y2 minus y1. So I could say y2 minus y1, that'd be y minus k. If I just want the radius then this would be it. But if I want to get rid of that radical, I could just square both sides to get my square root to go away. And when I square both sides, this is what I would come up with. And magically, that's the equation of a circle. So again, the equation of the circle just comes from performing the distance formula. And that gives me a way to help me remember the formula as well. So let's see what we can do with it. For the first one, they give me the equation of a circle in standard form, and they say, what's the center and what's the radius? Okay, so when we're looking for the center, remember that we said that's going to be HK, and the radius is going to be R. So I'm going to take that equation for standard form, and I'm going to lay it right on top of the equation that they just gave us and see if we can match it up. So when we're trying to find H, we can say X minus H, and if you'll notice, 2 is in the place of H, so we could say H is 2. Now, one thing you'll notice about that, originally this kind of looked like a negative 2 right here, and I ended up putting a positive 2 down here. A lot of people, when they see a subtraction sign, they think of it as the opposite of, and that's a really great thing to do with this equation. You could think of this as X, the opposite of whatever that number is right there. That's really helpful when I get down here to this next one. Because if I try and match this up, I can match up the y, but I can't match up the subtraction sign. K is not equal to 3. So if I look at this as the opposite of, I could look at this and say the opposite of positive 3 is negative 3. Or you could also think of this as y minus a negative 3. That would be how we got y plus 3. If you had y minus a negative 3, that'd be another way to see that k was equal to negative 3. So we want the opposite of whatever those numbers are there to be my center down here. Okay. Then you'll also notice that r squared lines up with 4. So if r squared is equal to 4, what's just plain r? 2, right. So my radius would be 2. So if they want me to graph that, I could come down here and say, okay, I'm going to go to my center, 2, negative 3. There it is right there. And my radius is 2. So I'm going to go 2 to the right, 2 to the left, 2 up, 2 down. And then just play dot to dot, right? So for that one, they gave me the equation and asked me to find the center and the radius. So now let's go the opposite way. What if they give me the center and the radius and they ask me to come up with the equation? Okay, so that's what's in this next example. For this next one, they gave me the center, negative 1, 2, and they gave me the radius, 4, and they asked me to create the equation. So I'm just going to follow my standard form up here. Okay, so this would be x minus what? X minus what? What's H? Yeah, it's a negative 1, so exactly. If I do x minus a negative 1, I'm going to end up with x plus 1. All right, then it would be y minus what? What's k? 2. So y minus 2 is equal to, now I have to be really careful with this. If this is supposed to be r squared and r is 4, am I going to take the square root of 4 or am I going to square 4? Fun, right? So one more time, r is 4. If I'm looking at this equation up here, it says take r and square it. I'm going to square that 4 and get 16. The reason I think that's so confusing to us, though, is that over here, we had to take the square root of the 4 to get the radius of 2, whereas over here we've got to square the 4 to get the radius of 16. So be very careful with that, because on our quiz next week, our quizzes are multiple choice. And on our quiz next week, I can promise you that on a problem like this, one of the answers sitting there would be equal to 16, and another answer sitting there would be equal to 2, so that I can see you know whether you're supposed to square that or square root that. Okay, so watch out for that. All right, look at example 9. Just going to get you started on this one, and I'm not going to go all the way through it with you, but just want to give you a head start on it. It says the point 3,4 lies on a circle whose center is at negative 1, 2, as shown in the figure. Find the equation for the circle. And so at first glance, that kind of seems like what we were just doing, find the equation. If I'm going to find the equation, though, they were giving me the center and the radius. I need both of those things. They gave me the center. What do I need? I need the radius, right. So I have the center. I need the radius. So now I got to figure out how I'm going to find that. Well, first off, the wording in example 9 is different from the wording on the homework problem. In example number 9, it says the point 3,4 lies on the circle, whereas in the homework it says 3,4 is a solution point. Those two things mean the same thing. It being on the circle and it being a solution point are the same thing. Here's what we mean by solution point. If it is a point that is a solution for your equation, if it's a solution for your equation, your graph goes through it, right? Like, think about how you graph a line. You go through and you find all the ordered pairs that are the solution for that equation. You plot all those and it makes the line, right? So if it's a point on the line, it's a solution to your equation. If this is a solution point for my equation, that means that it is on the graph of my circle, okay? So whether they say it's a point on the circle or it's a solution point, it means the same thing. So if this is a point on my circle and this is the center of my circle, how could I find the radius? I need a radius. How can I find it?
Solve for R.
I can solve for R. How can I do that? Close.
You manipulate the equations so that R equals distance.
I know what you're saying. Hang on, that's awesome. And yes, distance. And what you were saying, I think, was the idea of diameter, and then you could do the midpoint of that. Absolutely, that works as well. Those are all great ideas. Okay, so distance, I think, is probably our most obvious solution, where we could say, I have a point on the circle, I have the center of the circle. That's like up here. If I have the center of the circle and I have a point on the circle, the distance between them is the radius. So if I just used my distance formula, then I could come up with my radius. But what Mark said is fabulous too, because why couldn't we also, as an alternative to this, why couldn't we take the equation and just plug in the point that we know? If we plug in the center HK and we plug in the point we know XY, the only unknown then would be R, right? Two completely different ways. If you throw that idea of diameter in, three completely different ways of doing this. All of them would work. It's whatever feels most natural to you. So we're not going to actually finish solving this one out. I just wanted to kind of get you going in the right direction with this one, and then you can kind of pick which of those routes you might want to go to finish that one off. Okay? So here's your homework for tonight on pages 9 through 13. We're doing 43 through 63, every other odd. So again, that's do 43, skip 45, do 47, skip 49, do 51, skip 53. You get the idea? So skip every other one. And then 61, 65, 89, challenge 67.